Welcome back to the lecture series on GPU architectures and programming. So, just as a small recall, in the last lecture we have been discussing about three possible optimization techniques that you can do while writing a code for parallel reduction in a GPU architecture. So, we just picked up the problem and discussed a few optimization techniques. So, a small recap on the techniques we already discussed. So, the first was the very naive parallel algorithm. So, where we just used threads for doing their local computation. So, the first thing is that you just use the threads to load the data from the global to the shared memory, and then each thread is doing a sum of consecutive elements, and in that way what you are essentially doing is you are using thread IDs with alternate values. I mean, there are thread IDs differing in by 1 here, right, to add consecutive values, and you go to the next iteration. So, what is happening is in each iteration, I mean, half of the threads are going idle, and also in parallel the threads are doing the addition in strides which are increasing by a factor of 2, right. And the problems that we had with this implementation was as follows, like first of all, it was a highly divergent implementation. As you can see, due to this if condition, half of your threads inside the same warp is getting to diverge here at this point, and also you have a loop overhead, and you are doing a percentile computation that also has got some overhead, right. And so, these were the most important problems here. The first thing we do as part of optimization 2, in this case the reduction 2, I would say the first optimization here is that you make consecutive threads do the addition. So, if you remember the earlier picture, the thread IDs were 0, 2, 4 like that, but we do some program transformation and make consecutive threads take care of doing the addition. So, we have the other features constant, that means the strides keep on increasing in multiples of 2, but you are always working with consecutive threads. Due to this, you always have warps which are non-divergent, because all consecutive threads are always active most of the time. But the problem here is, as we can see, that you have a situation of shared memory bank conflict, which we can look into by studying the access pattern of the threads. So, every thread is accessing 2 consecutive values, and this will give rise to a two-way bank conflict for each thread here. In this example, the solution here would be that, okay, let's now change the way in which the threads access the corresponding values. So, if you just take a close look here we made consecutive threads work, but consecutive threads are working on two consecutive values from the shared memory, right. So, when the operation is going to happen, for each thread, first there would be a load, right, I mean for operand 1, load for operand 2, and then the addition, right. Now, here, since if I look at the access pattern for the threads, all the threads, the loads that we are going to do for operand 1, they are not consecutive. That is the basic problem, right. So, thread 0 is loading from here, thread 1 is loading from here, thread 2 is loading from here, as you can see. So, to be more specific, so thread 0 is loading from location 0, thread 1 is loading from location 2, thread 2 is loading from location 4, and all that for operand 1, right. So, that is the instruction that will fire, and when this instruction fires, all the threads in the warp, since they are not accessing exactly consecutive locations, so we have got this issue of the bank conflict here. But how do you remove that? Now, let us look at the access pattern of a transformed thread for a transformed operation here. So, let us look at the alternate code that we can have to resolve the bank conflict. So, now let us start saying that okay, let us arrange the threads in such a way that yes, I have consecutive threads working. So, that is removing the issue of divergence inside the warp. Also, we change the way the consecutive thread IDs access the memory. So, what we do is earlier thread ID 0 was accessing memory location 0 and memory location 1, but now let us make thread ID 0 access memory location 0, and the next element that it is going to access is sitting at an offset which is of size L by 2, right, where L is the total size, right. And the same is going to hold for all the consecutive threads. For all of them, they are accessing 2 operands who are sitting at a large offset here rather than accessing consecutive operands. So, what is the good thing? Now, see that we are trying to do a load followed by add operation. So, again we will just repeat. So, if I am looking at the SIMD instruction that will fire, so all the threads will first load operand 1, the threads will load operand 2, the threads will add. So, now if I look at the way the threads are going to load operand 1, I have that all the threads are accessing consecutive shared memory banks, all the threads in a warp are accessing consecutive shared memory banks, and that resolves the bank conflict issue which was earlier. So, just for clarity, let me just repeat again what happened here in the earlier scenario. So, here when all the threads who are consecutive ID from the same warp, no divergence, but they were loading operand 1, they were accessing locations with 1 hop, and that would effectively lead to the two-way bank conflict problem, which would occur for both of the loads individually, right. But now, when I write a code which is going to give me this kind of an access pattern, so I have consecutive thread IDs inside a warp, and they are all loading the operand 1 from the shared memory without any bank conflict, because all the threads are accessing all the banks in parallel, right. So, that is the good thing. So, this load will have no bank conflict. The second load where it is going operand 2, that also is not going to have any bank conflict, because again they are all accessing consecutive banks. So, I have removed the bank conflicts for both the loads, and then I have the usual addition. So, but now the question is, how do I write the code so that I can make it behave like this? Now, observe what was the earlier code. So, the earlier code started with a stride of 1, that is why the threads were loading consecutive IDs in the first iteration, then it was loading with a stride of 2 in the second iteration, then stride of 4 in the third iteration, so on and so forth, right. So, this was the kind of code that we are executing. But now, if I want this kind of an access pattern, that means I want all the operand 1s of consecutive threads to be also consecutive, all operand 2s of consecutive thread to be also consecutive, then I need each of the threads to start with the highest stride, and then in the next iteration the stride should reduce, right. So, here this is like this stride is half of the total array size, and then it should reduce by half, and then it should further reduce by half, like that, which would mean I do not count from the lower value of stride to the higher value in multiples of 2, rather I start the loop with the highest value of the stride and get down by each time dividing the stride factor by 2. So, if we continue like that, then this is what we get, right. This was the original reduction code. Now, I start with the highest stride, which is half of the block dimension, and in each iteration I reduce it by 2, right. Inside, all we are doing is we are checking whether the TID is less than the stride, because of course, I have started with the highest stride value. So, every TID that is going to really get into the loop will be less than this stride value. That, as you can see, that here the stride value is this much. So, the TIDs that are going to get into the loop should be up to this. In the next iteration, the stride value is this, the TIDs that should be active should be 1 less than this, so on and so forth, right. So, in this way we keep on continuing, and the loop will keep on executing, decreasing the stride value, and inside each iteration I have got all the threads getting half in number, but I also have in each iteration the threads who are consecutively ID'd in a warp, they do not diverge, and they also do not get into any shared memory bank conflict. I hope this is clear. With our example, sorry, this was earlier was reduction 2, this is reduction 3. So, I have the S, that is the stride value starting from the highest stride, keeps on decreasing, right, keeps on decreasing, and inside the loop every thread is doing the usual sum, and then again in the loop you decrease the stride, and again get in the loop, you count the sum with the stride decreased, and you keep on doing this. Now, let us look at an analysis of this code. So, as we can see that there is gradual reduction in execution time. So, here we have given some statistics considering an array size of 2 to the power 26 thread blocks of size 1024, which means I am calling the kernel multiple times and doing the reduction. I am using my reduction kernel 1, 2 or 3, whichever. In each iteration it is reducing the set of blocks, and with recursive call of the kernel finally I get to one value, right. So, the reduction code, when it reduces this entire array for a Tesla K40 GPU, as you can see these are the timings and these are the bandwidths. So, the timings tell me the total execution time considering this initial array size. So, of course, you can understand the timings are with respect to multiple kernel invocations, the number of kernel invocations are required for reducing the entire array, and and this bandwidth gives me the total number of loads and stores that have happened divided by the amount of time spent. So, what is the GB per second bandwidth consumed from the memory, right. So, as we can see with reduction of conflicts for the shared memory, I have higher bandwidth, and also I have reduced execution time as an effect of that, and primarily all the acceleration that is coming in is due to the increased memory bandwidth exploited by the code, and that actually is affecting the timing and reducing the timing here, right. I hope this is clear. Just to repeat again, the reduced timing that I am getting is basically due to the increase in memory bandwidth that the program is able to exploit, right. Now, still I would say that we have certain issues. What is that? First of all, this loop is still very expensive. Again, why do we call a loop as expensive? Just to be clear from our earlier discussions on basic architecture, every time your threads get into the loop, you have to check for the loop conditions, right. So, that is one branching check that you have to do before the threads are getting inside the loop. The good thing here is we have removed the module operation, and also the most important thing is half of the threads are idle on loop on first loop iteration. That means, initially after loading all the data from the global memory to the shared memory in every launch of the kernel, only half of the threads get inside the actual loop, right. So, this is the code that every loop is executing. What it is essentially doing, it is essentially this is the line of code that every loop executes before apart from just computing the global ID using the block dimension, block ID and thread IDs. And here you are, as you can see that we are just doing the load from the global memory to the shared memory. After that, immediately I am starting to use half of the active thread that I have inside the loop, right. As an alternative, just to increase the part thread activity, what I can do is I can increase the amount of computation that every thread has to do in the first iteration. As you can see, in the first iteration up to reduction 3 of our method, in all the methods reduction 1, reduction 2, reduction 3, there is not much activity to be done by each of the threads apart from the loads, right, after for one half of the threads. All they are doing is just the load in the shared memory, and after that half of the threads do not have any activity. Instead of that, what we suggest is we give more work for each of the threads by making them do some more additions, right. So, make busy all threads in the first half and halve the number of blocks. What do we mean is, let all threads not only load data from global memory to the shared memory, but all threads also do some reduction by themselves. For example, okay, maybe I make each thread load 2 data points from the global memory and then add them and then store into the shared memory. That is increasing the per thread activity. As a side effect, that is going to halve the number of blocks also, right? So I increase the per thread activity. I am, as a side effect, decreasing the number of blocks. So essentially, I am replacing one single load with 2 loads and an addition for all the threads, right? So this is the first step of the reduction, which we ensured that it is going to be done by all the threads together. So I mean, from a mathematical point of view, what's happening is you have too many threads that you have launched. You have launched too many threads here, and then you are suddenly increasing. I mean, you are using only half of them. So if I am trying to draw a picture representation here, so let's say I am launching these many threads. All of them just do the global load, and then half of them keep on working, right? So if I plot per thread activity, this is how things are really happening, right? Now with this step, what are we essentially doing? So then okay, let me keep the original picture here. So with this step, we are making it like this, right? Because I have increased the per thread activity here, and also this should be a bit, yeah. So what I am now doing is, okay, I am launching less number of threads, and these threads are only taking care of this part of the activity as well as the other activities, right? So I am launching this many number of threads, and they are taking care of the activities which earlier this half of the threads were doing. Now I don't launch them and increase the overall per thread activity by launching half number of threads and make them do more of initial work here. So that's the important point we are trying to make, that if we can find a nice balance between per thread activity and the number of threads, that is a good way to look into the issue of parallelism. So just to explain further, I have got some activity to be executed and I have launched too many threads, and I am not executing all the threads throughout the lifetime of the activity. So that doesn't make sense. Rather than that, I should try to do a load balancing here. I increase the amount of work to be done per thread and decrease the number of thread. Then since I am using less number of threads and utilizing them more, I will have less execution time, because I also put less overhead on the GPU scheduler and other resources in terms of context saving and doing the scheduling job of a higher number of threads, right? So the good thing is I don't use too many threads which are idle for most of the time, and in that way I save time in saving context and scheduling. So then if this was my original reduction 3 kernel, just have a look. This is the part of code which is now going to change, and it instead will become just like earlier it was just you load one global data point and store into one shared data point. Now each thread is loading 2 global data points and they are storing into the shared memory, right? That's all that is happening. So the analysis would be like this, that I have just increased the per thread activity. Due to that, I have a tremendous increase in the effective bandwidth usage, and as a result the further reduction in the execution time. So, I do not have this problem of half of the threads going idle on the first loop iteration now, but I still have this issue of the loop overhead, because every time I launch threads, they eventually get into the loop, and they have to, in every iteration of the loop, they have to check the loop conditions and all that. And now the another likely bottleneck can be the instruction overhead, because now I am executing more instructions per thread, but I can see that that's going to be a nice balance here. Now, the fifth reduction version is about the observation that I don't need this kind of synchronization barrier to be put in when I am executing the last warp. That means, when the number of active threads reduce to 32, then what happens? Then, as we can see that we have already removed the divergence from the reduction 1. That means, the threads that are active, they are now with consecutive IDs. So, they actually form a warp, right. So, since these threads are themselves forming a warp, and we know that warps execute instructions in lockstep from the programming point of view, and that would actually make this sync thread operations redundant here. So, this is not needed, and moreover, this check will also not be needed, that whether the TID is less than S is also not needed, because whatever the threads are there, which are going to work, the other threads are really not going to do any effective work, right. So, because I am finally interested with only the thread ID 0, which will give me the sum. So, at this point I do not need any of them. So, the good thing I can do is I can remove the sync thread and I can unroll the last 6 iterations. Why last 6 iterations? Because from 32, then 16, then 4, then 8, then 4, and like that, finally with 1. So, this last 6 iterations I can also save into the loop condition checking, right. So, the good thing would be that I simply remove the loop condition and all if conditions when the number of threads on which I require to focus changes to 32, and they all come inside a warp, right. So, then I will simply unroll this loop and write similar statements consecutively, and then I do not need this loop at all for those last 6 iterations. I do not need to check this loop condition, I do not need to do this if else check. So, without the unrolling, all warps execute every iteration of the for loop and the if statement, and this is what we can just remove by doing this unrolling operation. So, just recalling what we had in loop 4, this reduction 4 was that we were every time in the loop iteration we are checking this condition, and now we want to remove it. So, the alternate thing that we will do is, earlier this loop was executing up to stride greater than 0. Now, I make every warp go through this program, this for loop, as long as the stride is greater than 32, but once the stride variable decreases to less than 32, okay, once this stride variable decreases to less than 32 for the threads, then I do not let them get into the loop at all, and then I just make a call to this warp reduce function for all threads with the TID less than 32, and just forget the other threads here. So, as you can see, this code will be executed as long as S is greater than equal to 32. Once S is less than 32, I completely skip this loop, right. So, now the S is less than 32, and at that point I just check for the last warp, because that is what I am interested in. So, for the last warp I make a call here to this warp reduce function, fine. I hope this is clear. So, earlier what was happening is all threads were executing this loop, right. We have identified that once I am only at the last few stages of the reduction, where I have only 32 consecutive values to work with, and that would mean 32 consecutive threads to work with, 64 consecutive values and 32 consecutive threads to work with. I do not need to get into the loop anymore, because I will I will just write those statements in line one after another, avoid the loop condition, and more importantly I can avoid the sync thread here. So I execute this loop only up to s greater than 32. After that I am practically only interested in the TIDs which are less than 32, right? Because with s equal to 32, what will be interesting is the first 32 threads working on the 64 consecutive data points, which will be handled by this warp reduce function. And what it will do is, it will just, as you can see, I have just copied this body of loop in line one after another with decreasing value of s. So manually I am doing this without executing the loop here. I have completely hard coded 32, 16, 8, 4, 2 and 1. So here after this point I don't need, I am just repeating this part again. After this point, when s is I have executed the loop with s equal to 64. After that point I am only interested in the first warp. I leave all the other warps. I allocate the first warp to execute this sequence of statements, right? And as you can understand clearly now that this will be the thing that I am only interested in. I don't care about the other warps now. And so when I execute this sequence of statements, the advantage I gain is I don't have to execute this sync thread, I don't have to execute this for loops condition check and also the if condition check, right? So that would speed up the execution here, and then I just use the final thread to do the final sum, I mean to report the final sum from s data 0 to g data, the output data point in the global memory, right? So if I do an analysis here, then as you can see that this is further doing an order of magnitude reduction in the timing by unrolling the last warp. So this has been quite a successful optimization again with and this was also the result of increasing the bandwidth further, I mean effective increase in the bandwidth that we are getting for the same code, same array and same thread block choice. But still I have iterations and loop overhead, because although this has made the last warp go fine, but still for the previous warps I have this issue of loop overhead, and also I have these multiple iterations to execute, right? So what can be an alternative here? The alternative here is that if I can completely unroll the execution, I can remove the loop completely. But the issue is, why do I really need the loop? I need the loop that because at the compile time the number of iterations required is unknown, right? Because I don't know the block size or the number of threads on which a reduction kernel is going to be applied, right? Now if I take some static decisions that let us say I limit the block size to 5, 12 or 1024 threads, right? Because anyway it's going to be a power of 2. So if I know the block size, then doing a complete unrolling of the code is going to be easy, right? So in this case what we can do is we can take an advantage of C++ templates, and that is something that CUDA is going to support. So without getting into too much detail of what is a template and all that, we will just go through the example. Of course this is something advanced, so we will just give you an example here. So I mean you can consider this as a addendum to our original syllabus material. I mean this is just for the people who are more interested into the fundamentals of programming and further optimizations here. So instead of passing the block size as a making an implementation inside which I am handling a generic block size, let's assume that the block size can be specified as a function parameter, right? And or more I would say it's like a template parameter. Now what is the good thing then? So instead of having just the reduction kernel, I make a template of it with a parameterized block size. So what is the advantage? I will just tell what is the advantage of function template here. So if I have a template declaration here with parameterized block size followed by the usual reduced kernel, then the system will make multiple implementations of this function for different possible block sizes here. Actually, I mean I am adding more dynamism here, right? So essentially as you can see that if I decide that okay, the block size is limited by this size 512 or 1024 threads, then here since I am creating a function template here. So, what I will do is I will now do the reduction entirely through a sequence of if else blocks, completely remove the loop. So, this part is usual. You can just consider this as a computation of the global ID, and then okay, I think we have some. You can remove this. Yeah. So, you are computing this here the S data thread ID locations, and then you do the reduction in the shared memory using a sequence of if else blocks. So, you check what is the block size, and based on that you get into the corresponding part where you are starting to do the reduction. So, if the block size is greater than 512, then you will execute this block with threads that are of ID up to 256, I mean less than 256, right, because then you have a block of size 512 and you are going to use half of the threads to do the addition operations, right, like that, so on and so forth. So, that is how it is going to continue. So, essentially we have just unrolled the loop and we have just written a sequence of if else statements where the statement block will get activated depending on the block size. So, essentially the block size is being provided as a template parameter here, so that you have different versions of the code, and you have based on the block size the code will actually execute whichever is applicable, right. So, suppose your block size is 512, that would mean your code will start executing and will execute this entire sequence of if blocks, right, because that is what the loop will do, the equivalent loop will do, right. So, essentially with 512 you have how many in each iteration you have got so essentially you are going to compute with strides which is starting with 256, because block size 512, stride would be 256, and with that you will start the reduction. Just that code, as you can see, and every step the reduction stride size will decrease. All we have done here is we have simply replicated that behavior without the loop, right. So, we just put in the if else blocks. So, if block size is greater than 512, I start executing from this block. If the block size is not greater than 512, but greater than 256, greater than or equal to, then I just start writing it from this block, right. And why do I have this reduction by half? Because of the nature of the code, we know that the block sizes will be multiples of 2, and in every iteration it will be parts of 2, and in every iteration you are going to divide the stride by half. So, just have a close look into our earlier reduction kernels, look at the for loops and mentally unroll the for loop with the reducing value of strides and starting from a fixed block size, and this is the execution sequence which you are supposed to get. All we are doing is we are removing the loop, so that you are removing the loop check and you are just executing the internal behavior of the loop here, right. Because as you can see, everything else is same. At the end you again reduce the last var, but again you are using a function template parameter here. So, as I am repeating here, for our course purpose we do not assume that you will have knowledge of C++ or function templates. Consider this as just some extra interesting piece of code where we show that how using these function templates you can make good use of I mean you can actually make good use of this kind of templates to do further optimization with respect to reductions. So, this is the corresponding way when you are going to write a warp reduce function as in a template form, right. It's just the same, but what we are doing is you are essentially creating different versions of the function for different possible block sizes, right. So, if we do an analysis here, as you can see that since this approach is able to remove the loop and just unroll the execution of the loop as a sequence of if else blocks, a sequence of if blocks, it leads to further reduction in the execution overhead, right. So, I hope this is a bit clear to you. So, just to remember, the point to be taken in this case here is the issue with unrolling is I do not know what is my start size. So, instead of writing a function, I write a function template where I give the start size as a parameter, right. So, this can further be optimized with significant speed ups in practice, and the approach would be known as algorithmic cascading. So, let us try and understand what is this issue of algorithmic cascading. Now, earlier what we saw was that to increase the path thread activity, we just included some activity for all the threads initially. So, we did some addition on the global memory operands before doing before storing them in the shared memory and then proceeding with half of the threads, but that part is also configurable, right. So, I can actually do a combination of sequential and parallel reduction. So, each thread instead of loading and summing just 2 elements, it can do more activity, it can load and sum a sequence of elements, and then it can follow the idea of tree based reduction that we showed in shared memory. So, all we are trying to say here is instead of just doing one add and then storing the data in the shared memory. So, this, as you can see that this is a path thread activity. If we do not do this, then what do we really have? We have half of the threads working with the addition, and only initially all the threads were active in doing the load. With this, I increase path thread activity by doing one add globally on the data, right. So, this is a sequential addition performed by each of the threads on the data global data before storing it into shared memory. I am saying that we can increase the activity here. So, that would mean I can do some reduction on the global memory and then do the rest of the reduction on the shared memory, right. So, here and of course, since this is a path thread activity, this is going to be sequential. So, as you can see, there is a similar set of code here. This is a but this is sequential. So, each thread is doing computation on the global data that it has brought in, and then it is storing here into the shared memory. It is bringing in more data, and like that up to the grid size, right. So, essentially you are going to all you are doing is for each thread you are doing some part of the reduction sequentially in the global memory. So, you read from global memory and write to shared memory. Earlier you were doing only one addition, but here instead you are doing a sequence of some additions. So, if you start here with a thread TID, then you compute for this thread what is the global data it is going to bring, the data plus its block size, and then you make it work for some more iterations with respect to the grid size, right. You do instead of doing only one addition, you make it do multiple additions here, and with that you increase more amount of path thread activity, and that would give you further reduction by this step. So, just if you want to just go through this code here, let us have a look again. So, you are using this thread ID from your TIDX, right. So, then inside your block, what is this TID doing? So, this thread for its component of the shared memory, of course, you have defined the shared memory here, right, and then for this thread for its component of the shared memory is going to do multiple adds here from the global memory, as you can see. So, you are accessing the ith global location with the offset of a block size, right. So, you are going to add across this offset of a block size, and then you are going to put it here, right. So, just have a look into this. We will come back to this reduction again to get into the intricacy of this reduction. For right now, the basic idea we like to say is that earlier we just outsourced one path thread addition to all the threads for doing a global add, we are just trying to bring in some more sequential activity per thread to do our load balancing here, right. So, with this we will be ending this lecture. Thank you for your attention. From the next lecture, we will go into this in a bit more detail, and we will do a performance analysis of each of the reductions and continue with further topics. Thank you.